Okay, so let's talk about probability distributions for discrete variables. So the first thing we want to talk about are the variables themselves, and specifically random variables. And a random variable is simply a variable whose numerical value is determined by a chance mechanism. And so typically we denote random variables with the uppercase letter X or sometimes Y or perhaps additional letters. For example, let X be the total on a pair of dice. And so if you roll the dice, that could produce a total such as 7. So in that case, X equals 7 and so forth. And the thing you'll note there is that X is a number whose value depends on the outcome of a random experiment. And the outcome cannot be predicted. So by definition, it's random chance. When you flip the pair of dice, you could come up with any one of a number of outcomes. So most random variables, however, arise from random sampling. And a random sample is a sample that is selected from a finite population, but it's selected in such a way that all samples of the same size have the same probability of being chosen. So, for example, let's talk about birth order of children born in the United States in a given sample. So we have a probability distribution for the random variable X, representing birth order of children born in the United States. And that ranges from 1 all the way to whatever the maximum number of children is, perhaps on some reality TV show that we've seen, maximum number of children born in the US. And so the probability is going to range from the greatest probability for one child. So what's the probability that X, that a random child sampled, is birth order first, second, third, etc. That probability is going to be greatest for first. So we see a probability there of 0.416. Slightly lower for second, slightly lower for third, etc., until all the way down. And so all those probabilities are then going to sum to 1. And so first of all, if all possible values of a random variable are taken into account, the outcomes are exhaustive. So that means, first of all, as I mentioned, the probability of all outcomes must sum to 1 on that variable. And also mutually exclusive events can't occur simultaneously. So a given person can't have a birth order of first and second, for instance. There are really 2 types of random variables. The first type is discrete, the focus of this lecture. A discrete random variable is able to take on a countable number of distinct values in an interval, whereas a continuous random variable is able to take on any value in an interval, and we'll talk about that more in the second lecture. Okay, so let's talk about probability distributions for discrete random variables. Every random variable has a corresponding probability distribution, and that probability distribution describes the behavior of the random variable. And we're going to talk about 2 specific probability distributions for discrete random variables, and those are the binomial distribution and the Poisson distribution. So the purpose of the binomial probability distribution is to find the probability of a certain number of successes, so that's usually given the letter R, the probability of R successes given a fixed number of trials N for some random variable X. And so a great example of this would be the probability of getting 3 heads in 4 flips of a coin. So to use this distribution, the binomial distribution, the following 3 conditions must be met. First of all, there has to be a fixed number of trials N of an experiment with only 2 possible outcomes for each trial, and those are labeled success and failure. So in our example, flipping a head is considered a success, and we looked at 4 trials in that experiment. Second condition that must be met, the probability of a success on any given trial designated with the lowercase letter p remains constant from trial to trial. So when you flip a coin, the the probability of getting a head is always 0.5 if it's a fair coin, right? And the probability of failure also remains constant, and that's just 1 minus the probability of success. And the third condition that must be met, the trials are independent of one another, in that the probability associated with the outcomes in one trial aren't influenced by the outcomes in another trial. So when you flip a coin a second time, doesn't matter what you got the first time you flipped it, the probability is going to be the same that you're going to get heads in the second flip. Okay, so here are the equations for the binomial probability distribution. And so we're going to walk through this through this slowly. So again, here, if you look at the equation that's kind of in a shade of gray there, we're looking on the left-hand side for the probability that x, being our random variable, example the coin flip, equals r, which is the number of successes. So probability that some variable x equals a set number of successes conditional on two things. And that's conditioned on the number of trials, n, and then the probability of success on any given trial, which is designated by the letter pi there. And so this is equal to n choose r, you see in brackets there, that's the binomial coefficient, multiplied by pi to the power of r multiplied by 1 minus pi to the power of n minus r for any given number of successes r ranging between 0 and n. And so let's talk about this binomial coefficient here, referred to as n choose r. So that is equal to n factorial in the numerator divided by r factorial multiplied by n minus r factorial in the denominator. And that's the number of combinations of n things taken r at a time, again referred to as the binomial coefficient. So let's do an example here because I think it helps to see this. It's actually not as bad as it looks. So if our binomial coefficient consisted of 5 and 3, that would be 5 factorial divided by 3 factorial multiplied by 5 minus 3 factorial. So 5 factorial is simply 5 times 4 times 3 times 2 times 1, which equals 120. 3 factorial is 3 times 2 times 1 multiplied by 5 minus 3 factorial, which is the same as 2 factorial, which is 2 times 1. So the result in the denominator is 12. 120 divided by 12 equals 10. And so that's our answer for that part of the equation. You should also know that in the binomial probability distribution, the mean, which is often referred to as the expected value of x, our random variable, is equal to n times pi. N is, remember, the number of trials. Pi is the probability of success on any given trial. The variance of x is equal to n times pi multiplied by 1 minus pi. Okay, so let's walk through an example here. What is the probability of 3 heads in 4 flips of the coin? So I've repeated our formula there, and then beneath it shown how we would enter the actual values in the formula. So we're looking for the probability that x equals 3, that's the number of successes we're looking for, conditional on 4 trials and a probability of success on any trial equal to 0.5 or half. And so that's equal to 4 choose 3 multiplied by, in the binomial coefficient, multiplied by 0.5 because that's the value of pi, which is the probability of success on any given flip of the coin, to the power of 3 because that's the number of r is the number of successes we're looking for, multiplied by 1 minus 0.5 to the power of 4 minus 3, the number of trials minus the number of successes. So how would we calculate that? 4 over 3 equals 4 factorial divided by 3 factorial multiplied by 4 minus 3 factorial. You multiply that out, you get 24 over 6, which is equal to 4. Pi to the power of r, or 0.5 to the power of 3, is 0.125, and then again 1 minus 0.5 to the power of 4 minus 3 is just equal to 0.5. So you multiply that out, and the result is 0.25. So the probability of 3 heads in 4 flips of the coin is 0.25. Okay, and so what would the mean be? In this case, the mean would be 4 times 0.5 equals to 2, and the variance would be equal to 1. Okay, so the Poisson distribution, I'm not going to spend as much time talking about it. I just want you to know about it. I'm not going to ask you to do any problems, any mathematical problems based on the Poisson distribution. But I spent some time on the binomial distribution, so you probably will get a few questions about that. So if n is large, in the number of trials is large, and p is very small, the probability of success on any trial is very small, the binomial distribution is well approximated by this other probability distribution called the Poisson distribution. This distribution is used when there are discrete events that occur infrequently in time or space. It's also called the distribution of rare events. And you can see the formula there. Don't worry about memorizing that at all. The main thing to know there is the parameter lambda is the mean number of Poisson distributed events over whatever sampling medium is being examined. And so the mean, the distribution is equal to lambda, and the variance is also equal to lambda. So some examples that this might be used for, the number of arrivals at a checkout counter during a 5-minute period, the number of flaws in a pane of glass, number of breast cancer deaths in a given year, etc.